Okay, back to the whole idea of substitution reactions. And this time we're going to look at SN1 type of reactions. Ever so slightly different from the SN2, but that's mainly due to our starting material. What's SN1 mean? Substitution nucleophilic unimolecular. Now probably the easiest way to remember this is one thing happens at a time, as opposed to an SN2 where both things happen, the attachment of the new and the breaking of the old, happen together at the same time. So a reminder, here is the definition of a nucleophile. I've actually seen this as a question in an old paper. So don't forget, we've got a nucleophile is something that has unbonded electron pairs that can be used to form a new covalent bond. So we're probably talking about a dative bond here. Now, we tend to find this, if we link it again to our acids and bases topic, we find that Lewis bases tend to be nucleophiles. Think about it. Lewis base is something that has electron pairs or lone pairs that it can share. So some common examples are things like a chloride ion. Now this is not really drawn all that well, the chloride ion, but we can see it has 4 electron pairs waiting to be used. The other one is a hydroxide ion. In this case we've got 3 electron domains that are not being used in bonding and 1 electron domain in bonding. But it can also be a molecule. As we know, water has 2 pairs of unbonded electrons, and this gives it its bent shape. So we need to think about that on the way through. And ammonia is another good example of a nucleophile because it's got the lone pair that sit on top of the nitrogen. So what happens? If we look at this one, we see I've got a secondary structure. We've got the bromine attached to the central carbon in the chain. Now, we tend to find that if we have a tertiary structure, in other words, where the hydrogen is, we have a CH3 group or a chain structure attached, it is even better for this reaction. So that would be a tertiary structure is better than a secondary structure. And we saw that at the end of our last video on SN2 reactions. Alright, so what actually happens is after we have this, the polar bond, we actually get all those electrons in that polar bond and go to the leaving group. In our case it was bromine. So we've got this thing now where the carbon is deficient in electrons, right? But the CH3 groups are electron donating groups, and they will push electrons in to try to stop or to try to limit the effect of the positive charge on the ion. Alright? This makes it more stable. So we get a thing called a carbocation forming. The nucleophile, which is, of course is going to be lots of electrons, so it's negatively charged, will be attracted to this carbocation and slot in to form a bond. So 2 of the electrons on the hydroxide, the oxygen in particular on the hydroxide, will form a new bond with the carbon, and we will end up with this structure. Now we saw in SN2 reactions we get an inversion of the structure. In an SN1 we don't. It's like if you can imagine a busy car park. The new car that's trying to find a parking spot is the nucleophile. The car that is leaving a parking spot is the leaving group. And the nucleophile can only move in once the leaving car has gone, so the space is made available. That is probably one of the easier ways to think about it. Again, please know this for your tests.